Have you ever wondered what happened before the Big Bang? It's a question that has puzzled scientists and curious minds for decades. Today, we're going to explore this fascinating topic and challenge what we think we know about the beginning of our universe. The Big Bang Theory is our best explanation for how the universe began. It suggests that about 13.8 billion years ago, everything in the universe was packed into an incredibly hot, dense point. Then, in an instant, it started expanding rapidly, eventually forming the stars, galaxies, and planets we see today. But here's the thing. Many people think the Big Bang was the start of everything, that before it, there was simply nothing. However, this idea might not be entirely correct. Scientists have been working hard to figure out what might have existed before the Big Bang, and their ideas are pretty amazing. Our current physics understanding works well to explain most things in the universe, but when we try to look at the exact moment of the Big Bang, things get tricky. Our best theories, like Einstein's theory of gravity and quantum mechanics, don't work well together when we try to describe such extreme conditions. This is where the Planck epoch comes in. It's the earliest period we can talk about, with any confidence, lasting from the very beginning of the universe to about 10 to the power of -43 seconds after the Big Bang. That's an incredibly tiny amount of time, much shorter than a blink of an eye. During the Planck epoch, the universe was unimaginably hot and dense. It was so extreme that the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, might have been combined into one superforce. The universe was also incredibly small, possibly no bigger than a single person. Scientists are still working hard to figure out what happened during this time. It's like trying to solve a puzzle with most of the pieces missing. We need new ideas and better tools to peek into this mysterious period of the universe's history. Understanding the Planck epoch is crucial because it could help us answer big questions about how the universe began and why it works the way it does. One idea is called eternal inflation. This theory suggests that the rapid expansion of the universe, known as inflation, didn't just happen once. Instead, it keeps happening in different regions of space. Imagine our universe as just one bubble in a vast, ever-expanding foam of bubbles. Each bubble represents a different universe with its own Big Bang and set of physical laws. This means that while our universe had a beginning, the larger multiverse has always existed and will continue to create new universes forever. A different approach comes from the realm of quantum mechanics. Some scientists propose that our universe could have originated from a quantum fluctuation. In simple terms, even what we think of as nothing in space isn't truly empty. It's filled with tiny energy fluctuations that can create particles out of seemingly nowhere. One theory suggests that a particularly large fluctuation could have given rise to the entire universe. This idea implies that the universe could have emerged from a state of quantum nothingness, where the laws of quantum mechanics allow for the spontaneous creation of universes. Another intriguing theory is the cyclic universe model. This idea proposes that the universe goes through endless cycles of big bangs and big crunches. In this model, the universe expands from a big bang, eventually slows down, and then contracts back into a dense state, only to explode again in another big bang. This cycle repeats indefinitely. One version of this theory is called conformal cyclic cosmology, proposed by Roger Penrose. He suggests that the end of one universe can smoothly transition into the beginning of another, creating an eternal sequence of universes. In a cyclic universe model, the universe doesn't have a single beginning or end. Instead, it experiences a series of big bangs, where it expands, and big crunches, where it contracts back into a dense state. After each big crunch, a new big bang occurs, starting the cycle over again. This means that the universe could be infinitely old, with no true beginning or end. One of the key ideas behind this model is that the universe's expansion will eventually slow down and reverse due to gravitational forces. As it contracts, it heats up and becomes denser, eventually leading to conditions similar to those at the Big Bang. When the universe reaches this incredibly dense state, it bounces back and starts expanding again. leading to a new cycle of cosmic evolution. The Ekpyrotic Scenario. A specific example of a cyclic universe model is the Ekpyrotic Scenario. This theory was introduced by Justin Corey, Bert Ovroot, Paul Steinhardt, and Neil Turok in 2001. The term ekpyrotic comes from an ancient Greek word meaning conflagration or fiery destruction, reflecting the idea of a universe that is cyclically reborn from a fiery state. In the ekpyrotic model, the Big Bang was not the beginning of everything, but rather a transition from a previous phase of contraction to the current phase of expansion. This model involves the concept of brains from string theory. Imagine our universe as a three-dimensional brain floating in a higher dimensional space. According to the Ekpyrotic theory, our universe was created when two of these brains collided. This collision caused the Big Bang, and the matter and energy we see today are the result of quantum fluctuations from before the collision. After several billion years of expansion, the universe will eventually start contracting again, leading to another collision and a new Big Bang. This cycle can repeat infinitely, with each cycle smoothing out irregularities and creating a more uniform universe. Creation of a universe from nothing. Another fascinating idea about what might have come before the Big Bang involves quantum fluctuation. This theory leverages the principles of quantum mechanics to suggest that our universe could have emerged from what we might call nothing. In quantum mechanics, the concept of nothing is far from empty. Even in a perfect vacuum, where there are no particles or radiation, there are still quantum fields that permeate space. These fields are never truly at rest. They constantly experience tiny fluctuations in energy. According to the Heisenberg uncertainty principle, these fluctuations mean that particles can spontaneously appear and disappear, even in what we consider empty space. This phenomenon is known as vacuum fluctuation. It implies that nothing is a seething background of potential energy. Occasionally, these fluctuations can be significant enough to create particle-antiparticle pairs, which briefly pop into existence before annihilating each other. This process has been observed in experiments and is a well-established aspect of quantum field theory. When we talk about what came before the Big Bang, we run into a profound philosophical question. Is before the Big Bang even a meaningful concept? According to our current understanding of physics, the Big Bang wasn't just the beginning of the universe, it was also the beginning of time itself. This means that asking what happened before the Big Bang might be as nonsensical as asking what is north of the North Pole. The idea that time itself began with the Big Bang challenges our everyday understanding of cause and effect. In our daily lives, every event has a cause that precedes it in time. However, if time started with the Big Bang, there was no before for a cause to exist. This concept is difficult to grasp because our brains are wired to think in terms of linear time. Philosophers and scientists alike have debated this issue for centuries. For instance, St. Augustine argued that time was a part of God's creation, and therefore, there was no before the creation of the universe. Modern cosmologists, influenced by theories like general relativity, also suggest that time as we know it began with the Big Bang, making any discussion of before it meaningless. The Big Bang theory posits that around 13.8 billion years ago, the universe expanded from an extremely hot and dense state. This event didn't just create all the matter and energy in the universe, it also brought space and time into existence. Before the Big Bang, the universe was in a state where our conventional understanding of space and time breaks down. In this singularity, the laws of physics as we know them cease to function. During the earliest moments of the Big Bang, the universe was so compressed that the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single force. As the universe expanded and cooled, these forces separated, leading to the complex universe we observe today. This period, known as the Planck epoch, is crucial because it marks the boundary where classical concepts of time and space no longer apply. Scientists are working tirelessly to uncover the secrets of the universe's earliest moments. One of the most exciting tools in this quest is the James Webb Space Telescope, or JWST. This powerful space observatory uses infrared vision to peer back over 13.5 billion years, allowing us to see the first stars and galaxies forming. The JWST is helping us answer key questions about the early universe, such as when and how ionization occurred and what the first galaxies look like. Another crucial area of research involves studying the cosmic microwave background, the afterglow of the Big Bang. Scientists are using increasingly sensitive instruments to measure tiny fluctuations in the CMB, which can provide clues about the universe's early stages. Projects like BICEP3 and the Keck Array are gathering incredibly precise CMB data, searching not only for these fluctuations, but also for signs of gravitational waves from the early universe. As we conclude this exploration, remember that science is a constantly evolving field. The theories we've discussed today may be refined or even replaced as new evidence comes to light. That's the beauty of scientific inquiry. It's always pushing forward, always questioning, always seeking a deeper understanding of our universe.